Welcome to qnawire.
So we have a wheel that is rolling down from the top of the hill to the bottom. Now, if we want to find out the rolling or the angular speed when it reaches the bottom of the hill, so to do so, we can use conservation of energy. Now, let's find out. We know that when the wheel is at the top, there's no kinetic energy. All we have is the potential energy. So we don't have to worry about the kinetic part. And if we just say that the height is h, so the total energy at this point is mgh. But when the ball is rolling down and or sorry, the wheel is rolling down and reaches the bottom, uh, then we'll have the kinetic energy, but there's no potential energy if we set this to zero, or y to zero at this point. And so at this point, y is h. So when the wheel is around here, then all we have is the potential kinetic energy. But this kinetic energy will have two components because the wheel is rolling, so it will have a rotational motion, and then the wheel is reaching down to the bottom, so that's why it's a translational motion as well. So the total kinetic energy k should be equal to half of mv squared, where v is the translational velocity, and we add that to the rotational part, which is moment of inertia times omega squared, where omega is the angular velocity. And since it's a rolling without slipping condition, so we can set omega as v over r. Now, we need to figure out the masses. So we are given the mass density, and to find out the mass, so let's find out the mass of the rim first. So mr is mass of the rim. That should be equal to mass density times the circumference, which is 2 pi r, because it's a linear mass density. And for the spokes, it's going to be lambda times r, where lambda is the linear mass density and r is the radius. So what we can do here, we can try to calculate the moment of inertia. And to do so, we see that the total moment of inertia should be the moment of inertia of the rim plus I of the spokes. And for each spoke, I is, so let's call it is. I is 1/3 ms r squared. So we can get the total moment of inertia I as mt r squared plus 6 times 1/3 ms r squared. So that's the total moment of inertia. And if we now write down the energy conservation equation, we see that as we mentioned that here all we have is potential energy. So energy conservation equation will have mgh on the right, which is the top of the hill, and on the left, it will have the potential energy, and on the right it will have the kinetic part because there's no potential energy. It's going to be half of mv squared plus half of I omega squared, where I is this quantity right here. All right. Now we see that the total mass is mass of the rim plus mass of the spokes. So we can add them together and see that we get this expression right here. Now, if we put this expression in the energy conservation, because we need m here, so we get this quantity times gh, which is equal to mass of the rim plus mass of the spokes So this is the total mass, and then here this is the mass of the rim, and this is the mass of the spokes, and then we multiply that with r squared. And from there, if we simplify this expression, we see that omega is pi plus 3gh over r squared pi plus 2. And now if we use the provided values, we see that omega, or the angular speed, is 124 radians per second. Now we can do a little further calculation and find out the translational velocity. And we see that this, we multiply r, if we multiply the radius r with the angular speed, we see that the translational velocity is 26 meters per second. Now in part B, where it says that how does the um, so how does the answer change if the linear mass density and the diameter of the wheel were each doubled? So if we double the density, so let's call it, let's say density is doubled. So if we double the density, it will have no effect to the equation, because we see that in our final expression there's no dependency on lambda, or the energy density. So omega is independent of that. So for that case, omega will be unchanged. Omega will not change. And for the radius, now r is doubled. So if r is doubled, then we see that omega is inversely proportional to r, because g and h are constant, and these guys are constant as well. So we have omega proportional to square root of 1 over r squared, which can be written as omega proportional to 1 over r. So if omega is proportional to 1 over r, then doubling the diameter will result in change in omega, and that will be that will reduce omega by half. So omega will reduce by half. But if omega will reduce, but v will be unchanged, because we see that v is r, so we have twice r now because radius is doubled. But then omega is halved, so it will be omega by 2. So then we got rid of that, and we see that this is indeed this expression. So v will be unchanged, but omega will reduce by half. Thank you.